Our next topic is a fun one, reinforcement learning, and we can actually use this idea with an example of Pac-Man. We can actually create a little intelligent Pac-Man agent that can play the game Pac-Man really well on its own, and you'll be surprised how simple the technique is for building up the smarts behind this intelligent Pac-Man. Let's take a look. Let's talk about reinforcement learning. This is kind of a fun little concept here. You can think about it in terms of the game Pac-Man, one of my all-time favorites. So the idea behind reinforcement learning is that you have some sort of agent, in this case Pac-Man, that explores some sort of space. And in our example, that space will be the maze that Pac-Man is in. And as it goes, it learns the value of different state changes within different conditions. So for example here, the state of Pac-Man might be defined by the fact that it has a ghost to the south and a wall to the west and empty spaces to the north and east. And that might define the current state of Pac-Man. And the state changes it can take would be to move in a given direction. And I can then learn the value of going in a certain direction. So for example, if I were to move north, nothing would really happen. There's no real reward associated with that. But if I were to move south, I would be destroyed by the ghost, and that would be a negative value. So as I go and explore this entire space, I can build up a set of all the possible states that Pac-Man can be in and the values associated with moving a given direction in each one of those states. And that's reinforcement learning. So as it explores this whole space, it refines these reward values for a given state, and it can then use those stored reward values to choose the best decision to make given a current set of conditions. So in addition to Pac-Man, there's also a game called Cat and Mouse. That is an example that's used commonly that we'll look at later. And the benefit of this technique is that once you've explored the entire set of possible states that your agent can be in, you can very quickly have a very good performance when you run different iterations of this. So you can basically make an intelligent Pac-Man by running reinforcement learning and letting it explore the values of different decisions it can make in different states, and then storing that information to very quickly make the right decision given a future state that it sees in an unknown set of conditions. So a very specific implementation of reinforcement learning is called Q-learning, and this formalizes what we just talked about a little bit more. So again, you start with a set of environmental states. We're going to call that S. And possible states are, the surrounding conditions of the agent. So is there a ghost next to me? Is there a power pill in front of me? Things like that. And I have a set of possible actions that I can take in those states. We're going to call that set of actions A. And in the case of Pac-Man, those possible actions are move, up, down, left, or right. And then we have a value for each state action pair that we'll call Q. That's why we call it Q-learning. So for each state, a given set of conditions surrounding Pac-Man, a given action will have a value Q. So moving up might have a given value Q. Moving down might have a negative Q value if it means encountering a ghost, for example. So we start off with a Q value of 0 for every possible state that Pac-Man could be in. And as Pac-Man explores a maze, as bad things happen to Pac-Man, we reduce the Q value for the state that Pac-Man was in at the time. Okay? So if Pac-Man ends up getting eaten by a ghost, we penalize whatever he did in that current state. And as good things happen to Pac-Man, as he eats a power pill or eats a ghost, we'll increase the Q value for that action for the state that he was in. Okay? And then what we can do is use those Q values to inform Pac-Man's future choices and sort of build a little intelligent agent that can perform optimally and make a perfect little Pac-Man. So getting back to a real example here, some state actions here. Pac-Man, we can define the current state of Pac-Man by the fact that he has a wall to the west, empty space to the north and east, a ghost to the south. And we can look at the actions he can take. He can't actually move left at all, but he can move up, down, or right. And we can assign a value to all of those actions. So by going up or right, nothing really happens at all. There's no power pill or dots to consume. But if he goes left, that's definitely a negative value. So we can say for the state given by the current conditions that Pac-Man is surrounded by, moving down would be a really bad choice. There should be a negative Q value for that. Moving left just can't be done at all, and moving up or right are just neutral. So the Q value would remain 0 for those action choices for that given state. Now you can also look ahead a little bit to make an even more intelligent agent. So I'm actually 2 steps away from getting a power pill here. So as Pac-Man were to explore this state, if I were to hit the case of eating that power pill on the next state, I could actually factor that into the Q value for the previous state. And if you just have some sort of a discount factor based on how far away you are in time, how many steps away you are, you can factor that all in together. So that's a way of actually building in a little bit of memory into the system. So the Q value that I experience when I consume that power pill might actually give a boost to the previous Q values that I encountered along the way. So that's a way to make Q learning even better. So one problem that we have in reinforcement learning is the exploration problem. How do I make sure that I efficiently cover all the different states and actions within those states during the exploration phase? So sort of the naive approach is to always choose the action for a given state with the highest Q value that I've computed so far, and if there's a tie, just choose at random. So initially, all of my Q values might be 0, and I'll just pick the actions at random at first. And as I start to gain information about better Q values for given actions in given states, I'll start to use those as I go. But that ends up being pretty inefficient, and I can actually miss a lot of paths that way if I just tie myself into this rigid algorithm of always choosing the best Q value that I've computed thus far. So a better way is to introduce a little bit of random variation into my actions as I'm exploring. So we call that an epsilon term. So we have some value that I roll a dice, I have a random number, and if it ends up being less than this epsilon value, I don't actually follow the highest Q value. I don't do the thing that makes sense. I just take a path at random to try it out and see what happens. And that actually lets me explore a much wider range of possibilities and a much wider range of actions for a wider range of states more efficiently during that exploration stage. So what we just did can be described in very fancy mathematical terms. Conceptually it's pretty simple. I explore some set of actions that I can take for a given set of states. I use that to inform the rewards associated with a given action for a given set of states. And after that exploration is done, I can use that information, those Q values, to intelligently navigate through an entirely new maze, for example. Okay? But this can also be called a Markov decision process. So again, a lot of data science is just assigning fancy, intimidating names to simple concepts, and there's a ton of that in reinforcement learning. So if you look up the definition of Markov decision processes, it is a mathematical framework for modeling decision making. Decision making, what action do we take given a set of possibilities for a given state, in situations where outcomes are partly random, kind of like our random exploration there, and partly under the control of a decision maker, the decision maker being our Q values that we computed. So MDPs, Markov decision processes, are a fancy way of describing our exploration algorithm that we just described for reinforcement learning. And the notation is even similar. States are still described as S, and S prime is the next state that we encounter. We have state transition functions that are defined as P sub A for a given state of S and S prime. And we have our Q values are basically represented as a reward function. So a R sub A value for a given S and S prime. So moving from one state to another has a given reward associated with it. And moving from one state to another is defined by a state transition function. So again, describing what we just did, only a mathematical notation and a fancier sounding word, Markov decision processes. And if you want to sound even smarter, you can also call a Markov decision process by another name, a discrete time stochastic controlled process. Holy cow, that sounds intelligent. But the concept itself is the same thing that we just described. So even more fancy words. Dynamic programming can be used to describe what we just did as well. Wow, that sounds like artificial intelligence, computers programming themselves, Terminator 2, Skynet stuff, but no, it's just what we just did. So if you look up the definition of dynamic programming, it is a method for solving a complex problem, like creating an intelligent Pac-Man, that's a pretty complicated end result, by breaking it down into a collection of simpler subproblems. So, for example, what is the optimal action to take for a given state that Pac-Man might be in? There are many different states Pac-Man could find himself in, but each one of those states represents a simpler subproblem where there's a limited set of choices I can make, and there's one right answer for the best move to make. And storing their solutions, those solutions being the Q values that I associated with each possible action at each state. ideally using a memory-based data structure. Well, of course, I need to store those Q values and associate them with states somehow, right? The next time the same subproblem occurs, the next time Pac-Man is in a given state that I have a set of Q values for, instead of recomputing its solution, one simply looks up the previously computed solution, the Q value I already have from the exploration stage, thereby saving computation time at the expense of a modest expenditure in storage space. That's exactly what we just did with reinforcement learning. We have a complicated exploration phase that finds the optimal rewards associated with each action for a given state. And once we have that table of the right action to take for a given state, we can very quickly use that to make our Pac-Man move in an optimal manner in a whole new maze that he hasn't seen before. So reinforcement learning is also a form of dynamic programming. Wow. So to recap, you can make an intelligent Pac-Man agent by just having it semi-randomly explore different choices of movement given different conditions. Where those choices are actions, those conditions are states. We keep track of the reward or penalty associated with each action or state as we go, and we can actually discount, going back multiple steps if we want to make it even better. And then we store those Q values that we end up associating with each state, and we can use that to inform its future choices. So we can go into a whole new maze and have a really smart Pac-Man that can avoid the ghosts and eat them up pretty effectively, all on its own. It's a pretty simple concept, very powerful though, and you can also say that you understand a bunch of fancy terms because it's all called the same thing. Q learning, reinforcement learning, Markov decision processes, dynamic programming, all tied up in the same concept. So, I don't know, I think it's pretty cool that you can actually make sort of an artificially intelligent Pac-Man through such a simple technique, and it really does work. If you want to go look at it in more detail, here are a few examples you can look at that have some actual source code you can look at and potentially play with. So there's a Python Markov decision process toolbox that, wraps it up in all that terminology we talked about. There's an example you can look at, a working example of the cat and mouse game, which is similar. And there's actually a Pac-Man example you can look at online as well that ties in more directly to what we were talking about. So feel free to explore these links and learn even more about it. But that is reinforcement learning in a nutshell. So that's reinforcement learning. More generally, it's a useful technique for building an agent that can navigate its way through a possible different set of states that have a set of actions that can be associated with each state. So we've talked about it mostly in the context of a maze game, but you can think more broadly. And whenever you have a situation where you need to predict behavior of something given a set of current conditions and a set of actions it can take, reinforcement learning and Q learning might be a way of doing it. So keep that in mind.